Hello students, in lecture number 13 and 14 we discuss about the Fourier series representation of periodic signals, and in this lecture we are going to represent some of the signals in as a linear combination of complex exponential. So just to review the last lecture in one slide, that we had three equations, one which is actually synthesis equation, which is actually the representation of x of t as a linear combination of complex exponentials, and where ak here is the analysis equation. It is the Fourier coefficient, or they are called spectral coefficients of x of t, right? And a of ak can be calculated using this integral, and when k is 0, this is a naught. A naught is basically the DC component, right, or the average value of x of t, right, and it can be determined using this integral, right. So we will be using these equations in the examples that are coming in later slides. Now let us consider this periodic square wave, right. It is periodic because it is repeating itself after fixed intervals, right? And we have to find out the Fourier series representation of x of t, and the mathematical function of this square wave for one period is given by this equation, right? So x of t is equal to 1. This magnitude of each pulse is 1, right, when it is high, and when it is low it is 0, right? So magnitude of the pulse is equal to 1 as long as the time is between t1 to minus t1, right? You can see here, when time is between minus t1 to t1, the magnitude of the pulse, or the value of the function x of t, is simply 1, and it is 0 elsewhere. So this is a definition of this function for one period, which is from minus t upon 2 to t upon 2. This is one complete period, right? And this t upon 2 to 3t upon 2 is maybe another period, right? And you can take any one period, fundamental period, and represent this period as a linear combination of exponentials, and which would be same for the rest of the period as well. So now we are taking this fundamental period as a function, and we have to find out the Fourier series representation of this. Alright, so as I told you that we are going to consider this period to compute the Fourier series representation, and in this period, let me repeat again that that starts from minus t upon 2 to t upon 2, and in this period the value of function is 1 as long as the time is between minus t1 and t1, and it is 0 elsewhere, right? So first we need to find out the DC component a naught, and the formula for a naught is equal to 1 upon t and minus t upon 2 t of 2 x of t, right? So it is basically the integral of x of t over one period, and we know that x of t is 0 for some portion of the period which is between minus t upon 2 to minus t1, it is 0, and from t1 upon t upon 2 it is again 0, right? So we can rewrite the limits as minus t1 to t1, because from minus t1 to t1 the value of x of t is non-zero, right? Otherwise it is 0. So rewrite. Now we can further evaluate this integral by taking integral and substituting the limit. You get a naught equal to 2t1 upon t, which is basically the average value of the square wave. Now next thing is to find out the value of Fourier coefficient ak for the values of k not equal to 0, right? So the formula for ak is 1 upon t, and t naught to t naught plus t exponent minus jk omega naught t into x of t. Now you can substitute the values. Now the integral limit is minus t1 to t1, again for the same reason that from minus t1 to t1 the x of t is non-zero, otherwise it is 0, right? and minus t1 to t1, it is in fact equal to 1. So we have to evaluate the integral of this exponent from minus t1 to t1. Alright, so the integral of exponent is given by this equation, and in fact integral of exponent is the function divided by the power of exponent, and then we have to substitute the limits, right? So upper limit first and then minus lower limit. So substituting the limit, upper limit minus lower limit, and we can actually simplify it further, right? You can see that we have e power minus j k omega naught t1 and minus e power j k omega naught t1, and we have j in the denominator, right? So it looks like that we can convert this exponential divided by j as a sine function, right? We can represent this as a sine function. So let us rearrange some terms by taking j inside the bracket and dividing and multiplying it by 2, right, and taking minus common from here, right? So minus is common from here, and we have divided and multiplied with 2, and j is brought into the bracket in the denominator. So now you can see this one actually is a sine function, right? So it is we can rewrite this as 2 sine k omega naught t1 divided by k omega naught t, right? So this is the actually value of ak, and you can see that it looks like a sinc function. If you remember, sinc function is a singularity function, right? Sine x upon x, right? So ak is basically a sinc function. Here omega naught is equal to 2 pi upon t, and substituting omega naught in the denominator, we can actually further simplify it. When we substitute omega naught equal to 2 pi upon t, t would be cancelled with t, and we will have only pi k in the denominator, because this 2 would be cancelled with the 2 in the numerator, right? So t would be cancelled t, and 2 would be cancelled with the 2 in the denominator. So we'll get sine k omega naught t1 divided by pi k. So this is actually a simplified version of ak. Now in this function, t is basically equal to 4t1, right? Because this is one t1, another t1, and the third t1, and then 4t1, right? So the function is on for 2t1 and it is off for 2t1, right? So it is basically a 50% duty cycle, right, in this square wave. So t is basically 4t1. So omega naught t1 would be equal to omega naught into t upon 4. Using this equation, write down t1 as t upon 4, or omega naught we know is equal to 2 pi upon t, right? So omega naught t1 is simply equal to pi by 2. Now we can rewrite the sinc function that we obtained in the last slide as ak sine, and in omega t1 we write down pi by 2 multiplied by k divided by pi k. Now let us find out the value of Fourier coefficients for different values of k. For k equal to 0, we know a naught is equal to 2 t1 upon t, and we know t1 is equal to t upon 4. So a naught is simply equal to 1 upon 2, which is 0.5. Now in this function, let us substitute k equal to 1, right, and find out the value of a1. So substitute the k equal to 1, you will get sine pi by 2 divided by pi, right? So sine pi by 2 is 90 degree, sine of 90 degree is 1, right? So it is simply equal to 1 upon pi. And similarly, put k equal to minus 1, right? When we could put k equal to minus 1, sine of minus 90 is again minus 1, right? Sine of minus 90 is minus 1, and it is divided by minus pi because k is minus 1, so it's again 1 upon pi, right? So for k equal to 1 or plus 1 or minus 1, a value of a1 and a minus 1 is 1 upon pi. Similarly, I put value of k equal to 2 and minus 2, right? So for k equal to 2, you get sine pi divided by 2 pi, right? Sine pi divided by 2 pi, and sine of pi is 0, right? So whether you put k equal to 2 or minus 2, you get 0. So a2 and a minus 2 are equal to 0. Similarly, put k equal to plus 3 and minus 3, right? So for k equal to 3, you get 3 pi by 2, and sine of 3 pi by 2 is 1, and you get here 3 pi, right? So for k equal to plus 3, you get minus 1 upon 3 pi, because k sine of 3 pi by 2 is minus 1 and divided by pi. And similarly, for a equal to minus 3, you get sine 3 pi by minus 3 pi by 2, which is equal to 1 and divided by minus 3 pi. So for k equal to plus minus 3, you get minus 1 upon 3 pi. Similarly, for plus minus 4, you get 0, and plus minus 5, you get 1 upon 5 pi, and plus minus 6 would be 0 again, plus minus 7, you get 1 upon 7 pi, right? And if you plot different spectral coefficients for different values of k, you will get this spectrum, right? This is called the spectrum of square wave, right? Spectrum means what kind of frequency component it contains, right? So you can see it contains frequency, zero frequency, which is DC component, right? It is actually the highest one. Then the second highest one is the fundamental frequency when k is equal to 1. This is fundamental, first harmonic, or fundamental frequency, sorry, not the first harmonic, but this is fundamental frequency. Then second harmonic is 0. Then third harmonic is the third highest, and then similarly fourth harmonic is 0. The magnitude of fifth harmonic is smaller than a3, and similarly sixth harmonic is 0, and so on. So this is we can say it is the spectrum of square wave, and it is equal to t equal to 4t1 when we have 50% duty cycle. Now we can represent x of t as a linear combination of complex exponentials using this equation, and now we have to substitute the different values of Fourier coefficient for different values of k, right? So for example, first point would be k equal to 0, which is a naught, right? So when k is 0, e power 0 is 1, and the term that will get is only a0, right? So a naught is the term when k is equal to 0. Similarly, these terms after a naught are positive values of k. For example, k equal to 1, k equal to 2, k equal to 3, k equal to 4, up to k equal to infinity. And terms before a naught are negative values of k. This is k equal to minus 1, k minus 2, minus 3, up to minus infinity. Now we can substitute the values of Fourier coefficients. For example, a naught is 1 upon 2, similarly a1 and a minus 1 are 1 upon pi, and so on. So substituting all these values will give you the Fourier representation of x of t, right? Now we can simplify it further by grouping same harmonic components together. For example, putting fundamental frequency components together, then the third harmonic components, then fifth harmonic, and so on. So by doing that, we can actually further simplify it, because this function can be represented as a trigonometric function using Euler's formula, and similarly this one, and that one as well. So in order to represent this using cosine function, we have to have 2 here in the denominator, right? So in order to do that, we have to multiply 2 here. Now we can write down this function as a cosine of omega naught t. Similarly, this is cosine of 3 omega naught t, and so on. So this is what we get after simplification, and this is actually representation of x of t in terms of trigonometric function cosine, right? So we have DC component 1 upon 2, then we have fundamental frequency, then third harmonic, fifth harmonic, and seventh harmonic, and so on. Now the one in the orange color is the actual rectangular pulse, and x of t here is actually approximation of this one in the blue color, right? So approximation includes the DC component, which is 1 upon 2, and the fundamental frequency component, which is 2 upon pi cos omega naught t, right? So you can see approximation is not very accurate, right? So if we keep adding the terms, we will see that the accuracy approximation would keep increasing. Now we have added the third harmonic component as well, right? So you can see that now it is getting bit accurate. Similarly, we will add more components. Here we have added fifth harmonic component, and the result look like somewhat more accurate than the last approximation. Then we have added harmonic components up to 15, right? So you can see that the shape of the approximated waveform is getting closer to the square wave. Now after adding 50 harmonics, we see that the shape is getting closer to the square wave, and after 100 is pretty much accurate, right? So in this way, if we add infinite number of terms, we get exactly the rectangular pulse. Alright, so the Fourier series that we have found in previous slide was when t equal to 4t1, right, which was actually 50% duty cycle. Now if we increase t and keep t1 constant, right, so increasing t and keeping t1 constant is actually reducing the duty cycle, right? So when t is equal to 8t1, so this is 25% duty cycle, right? So what happens to the spectrum when duty cycle is 25%, right? So omega naught t now would be equal to pi by 4, and previous when 50% duty cycle, omega naught t1 was equal to pi by 2. So now ak would be equal to sine pi k upon 4 divided by pi k, and a naught would be equal to 1 upon 4, and find out how the spectrum of the square wave with 25% duty cycle would look like, right? So if you remember the spectrum of square wave with 50% duty cycle, the first DC component and the first harmonic were the dominant, right? Here you can see the power of the spectral components is more distributed among the higher harmonics, right? So this is what happens when we reduce the duty cycle, right? Similarly, cycle to 12.5%, right? So you can see that power is now evenly distributed among all the fundamental frequency components, right? So when duty cycle is higher, the power can be found in DC and the fundamental harmonic fundamental frequency component, right? And when duty cycle is reduced, you can see the power is being distributed among all the frequency components, or in other words, other harmonics are getting stronger, and the fundamental frequency component and the DC component is actually getting weaker. Now the example number 2, very familiar one for the electrical engineers, is the output waveform of a full wave rectifier. This is how the output waveform of a full wave rectifier look like, and it is basically pulsating DC, and output is represented as V of t, and the peak value of the output is V, represented by V, right? So it has a fundamental period from 0 to pi, and the equation of this waveform can be written in this form: V of t equal to V sin t, where t is between 0 to pi, right? So let us find out the Fourier series representation and then draw the spectrum and see what frequency harmonics are actually present. So in order to do so, we have to find out the Fourier coefficients a, k, a naught, right? So first we'll find out the DC component. Here the fundamental period is equal to pi, therefore omega naught is simply equal to 2. So DC component a naught can be determined by taking integral of v sin t over one period which is 0 to pi, right? So evaluating the integral and substituting the limits, you get a naught equal to 2v upon pi. So the average value of output of full wave rectifier is 2v upon pi. Now find out the value of Fourier coefficient for values k not equal to 0. The formula for that is this one: a k equal to 1 upon t exponent multiplied by x of t and integral for one period, right? So here one period is pi, 1 upon pi 0 to pi e power minus j. Omega naught is equal to 2, right? And kt v sin t and dt. So v is constant, it can be taken out of the integral, and we can represent the sine wave as a complex exponential, right? We can using Euler's formula. Sine wave is basically equal to e power jt minus e power minus jt divided by 2j. So 2j is taken out of the integral here. So now we have this. Now you can multiply this exponent with this one and this exponent with this one, right? We can actually multiply these exponents together, and from this multiplication of these two we have taken jt common, and from multiplication of this and this we have taken minus jt common, right? Now we can take the integral of this one and substitute the limit, minus integral of this one and substitute the limit. Now we can solve it further by evaluating the integral, and after evaluating integral we'll get this. The integral of this function came out to be this e power jt into 1 minus 2k divided by j 1 minus 2k, and similarly the integral of this came out to be this one. Now we can evaluate the limit of the integral. So putting the upper limit first and then minus lower limit divided by the constant, plus again substituting the upper limit minus lower limit. Now this function e power j pi into 1 minus 2k, since k is integer, so its value will always be minus 1. For example, if we substitute k equal to 0, we get e power j pi, right? So e power j pi is equal to cos pi plus j sin pi, right? So value of cos pi is minus 1 and sin pi is 0, and similarly this one would also be minus 1 for any value of k, right? So for example, we substitute k equal to 3, right? So this would be 2 into 3 6, and the function would be e power minus 5 pi, right? So e power minus 5 pi would be cos 5 pi plus minus j sine 5 pi, right? So cos 5 pi is again minus 1 and sine 5 pi is equal to 0. So for all the values of k, e power j into 1 minus 2k is minus 1, and similarly this one is also minus 1. So rewriting ak, and instead of this without wrote now minus 1, can so minus 1 minus solve 1 it minus further 2, and similarly this by multiplying minus j 2 with this and with this as well. So we know j square is equal to minus 1, so minus in the numerator and minus in the denominator would cancel each other. Now we can take 2 common from here and divide that 2 with this one, right? So 2 in the numerator and the 2 in the denominator will also be cancelled. Now taking LCM and simplifying it further would give you this result: a k equal to v upon pi into 2 upon 1 minus k square. And further simplification by multiplying v numerator with the numerator and denominator with the denominator will give you this result. Now the Fourier series of this function can be written in this form: k equal to minus infinity infinity a k into e power j k omega naught k. And if we plot the spectrum of this function a k for different values of k, you will see that the highest the power is in DC component, and the other second highest is the fundamental frequency component, this one, and harmonics are getting weaker. So from this figure, from this analysis, you can determine that the output of full wave rectifier still contains some harmonics. As you can see, it should be ideally be all the power should be in DC component, right? But however, it is not purely DC, therefore we still have some harmonics in this. And there is some exercise problem for you. We have now a bipolar square wave. It has negative value and the positive value as well. Unlike the example number 1, it has only positive value. So average value in this case should be equal to 0. A naught should be equal to 0. So you have to define the Fourier series representation and draw the spectrum. And similarly, is another example. It is a discontinuous function having 3 values, and one complete period is equal to 4 seconds, which start from 0 to 4. And find out the Fourier series representation of this triangular waveform. It is also periodic, so consider only one period, right, from for example 0 to pi, right, and the maximum value of triangular wave is pi by 2. So that is end of exponential Fourier series. Now we have another version of the Fourier series, which is called trigonometric Fourier series, and this was the actual version that was used by Fourier himself. So trigonometric Fourier series is actually exactly same like the exponential Fourier series, only the way of representation is different, right? So if we replace exponent by trigonometric functions using Euler's formula, you can get this type of representation, right? So in this Fourier series, x of t is equal to a naught, which is again DC component, and k equal to 1 to infinity. Then we have a cosine function multiplied by ak and sine function multiplied by bk. So now we have 3 coefficients to determine: one a naught, which is DC value, then coefficient of cosine function ak, and then coefficient of sine function, which is bk. So the formula for a naught is same, and to determine ak we have integral of x of t multiplied by cos omega naught t over one period, and similarly to determine bk, we have to find out the integral of x of t into sine omega naught t over one period. Right. So this is more time consuming, because we need to find out three coefficients, right? So in exponential Fourier series, however, we have to only determine one coefficient ak, that is sufficient for entire function, but in trigonometric Fourier series we need to find out three components. But anyway, the end result, the spectrum that you will get would be same. Only way of either using trigonometric functions or exponential functions, that depends upon the suitability of the application. For example, when you are dealing with the eigenfunctions, differential equation and solutions, then representing it by exponential function is suitable, because it is mathematically convenient. However, if you are trying to analyze in frequency domain, trying to analyze the signal in frequency domain, then trigonometric functions are better choice. So that is end of this lecture. If you have any queries, you can send me on my email address. Thank you very much.